Hey everybody, welcome back to chemistry. And today what we're going to do is some problem solving where we take the percent composition of the elements by mass and convert it to an empirical formula. And if we have the molar mass of that compound as well, we can convert that to a molecular formula. So let's get started. So here I have a slide that sort of explains how to take the percent composition by mass and get it into empirical formula. It's like 3 or 4 steps, so let me go over that. So the first step is what you want to do is you want to take any numbers that you see as percentages and just convert them to grams. Just take the same number and convert it to a gram. That is possible because remember the percentages we have are by mass. So those mass ratios should be the same whether you use percentages or grams. So just convert the numbers to grams, and so that makes things a little bit easy. Then once you've done that, make sure that for each element, once you have it in grams, you're going to have to use the molar mass to convert it into moles. And then after that, you sort of have a relative mole ratio of the elements. And so the next step is to look at those numbers of moles between the 3 different or 4 different elements, how many you have, divide it by the smallest number. And then once that is done, hopefully that will give you integral values, but it may not. And if it doesn't give you integral values, then what you have to do is multiply those numbers by some kind of integer such that those numbers are converted to integral values. And once you are at integral values, then you have an empirical formula. So I'm going to do a bunch of problems so we can sort of get used to this. Okay, so the first problem is what is the empirical formula of a compound that has the following percent composition by mass? And so we have a compound here, and we have potassium, manganese, and oxygen. And so we have some percentages there. So we have 24.75% potassium, we have 34.77% manganese, and we have 40.51% oxygen. Okay, so the first step is to just take those numbers and convert them to grams. So I'm just going to go ahead and do that really fast. So we have 24.75 grams of potassium, 34.77 grams of manganese, and 40.51 grams of oxygen. Okay, so we have sort of a mass ratio in the compound, but we got to get this into a mole ratio. So you convert each of these mass amounts into moles using the molar mass. So I think I have the numbers listed there for molar masses of the elements. So potassium is 39.098 grams. Grams should cancel out. Manganese is 54.938. And oxygen is 15.999. So let me, as quickly as possible, figure out what these numbers are in moles. So hopefully you can be able to do this. 24.75 divided by 39.098, and so we get 0.6330. I'll just do out the 4 significant figures for now, that'll be fine. 34.77 divided by 54.938, and we get 0.6329. And the next one is 40.57 divided by 15.999. Okay, so we have 2.535. I'll make it 6. Okay, so far so good. So what do we have here? We have a relative mole ratio of these elements. So let me just indicate that this is moles potassium, this is moles manganese, and this is moles oxygen. Okay. So what we want to do is we want to try to convert these to integral values. And so the first thing you should check is just divide these numbers by the smallest number. So I'm going to, the smallest number here is 0.6329. There it is. And so we divide all these numbers by 0.6329. So let's see what happens. Okay, so obviously with manganese, you're just dividing it by itself, so this number is exactly 1. Okay, how about 0.6330? I think you divide by 0.6329. I think you can guess what that's going to be. So it's 1, 0, 0. Okay, well, let's add another 0 there. Okay, 4 significant figures. Okay, 2.538 for oxygen, or excuse me, 2.536 divided by 0.6329, and we get 4.01. Okay, so what you can see is that now for the molar ratios of potassium, manganese, and oxygen, we have values that are very close to integers. So at this point, once you're close to integers, say like within 5% of an integral value, you have it, you're done. So all values have to be integral values. So at this point, we are done. So we can write out an empirical formula for this compound. So there's 1 of potassium, 1 of manganese, and 4 of oxygen. And you know, of course, that you should never have subscripts of 1. So really the empirical formula in this case is KMNO4. Okay, let's move on to the next one. The next problem, diethylene glycol used as antifreeze has a composition, and we have percentages for carbon, hydrogen, and oxygen to determine the empirical formula. So let's try this. And what I'm going to do, just to conserve on room, is I'm just going to take the numbers for percentages and write grams beside it, because that's what you would do. So carbon is 45.27 grams. Hydrogen is going to be 9.50 grams. And then oxygen is going to be 45.23 grams. Okay, so you know by now that the first thing you want to do is get this into moles for each of these elements. So it's times 1 mole over the molar mass of elemental carbon, which is 12.01 grams. Hydrogen is 1 mole over 1.008 grams. That's the molar mass of hydrogen atoms. Oxygen atoms, 15.999 grams. And so, okay, so let's go ahead and convert these numbers into moles and see where we're at. Okay, 3.769. Okay, so at this point, what we want to do is to see if we're close to integral values for these moles of these elements is just divide by the smallest one here. And the smallest moles is oxygen. So we divide them all by 2.827. So if moles oxygen, that should be exactly 1. 3.769. This is 1.33. Add another 3 there. Okay, so the question is this. With these moles of carbon and hydrogen, are we, say, within 5 or 10% of an integral value? And you can see that we're not. So we don't have the empirical formula quite yet. So let's talk about what we do next. So we can see that we do have a relative mole ratio. And so what we want to do is multiply by integers and see if we can increase this such that all the subscripts will be just integral values. So right now we have C 1.33, H 3.344, and then O is going to be 1. Okay, so let's think about what we do next. So let's just try in our minds multiplying all these values here by 2. Let's see what would happen. So if you multiply these values by 2, carbon would be 2.666. Is that an integral value? No, it's not. So hydrogen would be 6.6 something. Is that an integral value? No. Oxygen would be 2, so that would be good enough. So multiplying by 2 is not good enough to bring this to a suitable empirical formula as represented by integral values. Let's try multiplying by 3. If you take 1.333, I already did this on my calculator, that's very near 4. So it's going to be carbon 4. If you take H 3.344 and multiply it by 3, you're going to end up hydrogen being around 10. If you take the 1 subscript by the oxygen, multiply that by 3, that's going to be 3. So what we did is we took this mole ratio and just merely multiplying these numbers here in the mole ratio by 3, we were able to come up with integral values or very near integral values. And so once you've done that, you are done. This is a suitable empirical formula. So the empirical formula for this compound is C4H10O3. Okay, let's move on. Problem 3, 5 grams of manganese oxide contains 3.16 grams of manganese. Can you identify the oxide? Okay, so this is a little bit of a different problem in that we don't start out with percentage values, but you can see that we are starting with mass values that we can convert to moles. Now, it's a little bit strange in that we are not given all the values for masses for the elements that are there. So we are given a mass value for manganese, so let me write that down. We have manganese, and it's 3.16 grams. Now, we are given a little bit of additional information, and that we're told that this compound is something called a manganese oxide. So if you see that, what you can probably bet is that there are really only 2 elements in the compound. There's manganese and there's oxygen. And we are given a mass for the manganese oxide. So the manganese oxide, we don't really know what the subscripts are for this compound. That's what we're trying to figure out. We're trying to figure out an empirical formula. So we could write manganese with an X here if we want to. X representing the subscript for manganese we're trying to find, and an oxygen with a Y subscript. Okay, so we are given a mass for the manganese oxide, so it's 5.00 grams. So this is a manganese oxide, so any mass that is not in manganese will be in oxygen. So all you have to do to find the mass of oxygen in this compound is just to take the 3.16 manganese mass, and subtract it from the 5 grams of oxygen mass, and that should be the oxygen mass. Should have said manganese oxide mass. Okay, so 5 minus 3.16 is 1.84 grams of oxygen. Now at this point, what we've been doing before, we can do again to get an empirical formula. So let's go ahead and try this. So we have a mass of manganese. We want to get this into moles. Divide by the molar mass again, which is 54.938. Oxygen, okay, let's see what we get. Okay, so at this point, you divide these numbers by the smallest number. So for manganese moles, we're now at 1. Let's see what oxygen moles are. So it's going to be 0.1150 divided by 0.0575. Ooh, exactly 2. Boy, that was lucky. Okay, So basically, we're now at integral values. We can stop. We have an empirical formula here. So the empirical formula for this compound is MnO2, meaning the X, the subscript for manganese, is 1, and the Y for oxygen, the subscript for oxygen, is 2. Okay, let's move on. Now, what we're going to do is we're going to sort of extend what we've learned, and there will be cases, perhaps in your problems on your homework or on your test, where you're given maybe percentage of elements by mass for a compound, and you're not asked to get an empirical formula. You're asked to get a molecular formula. So that's a little bit more complicated of a problem. So one of the things we sort of have to get used to is sort of the relationship between an empirical formula and a molecular formula. So let's talk about what that is. So you might recall with an empirical formula, what that was a case where you had numbers in the smallest whole number ratio, and you got that from the molecular formula by dividing by some number, right? So the molecular formula should be some multiple, some number, some multiple n on the screen of the empirical formula. So you have to figure out what that value of n is. And then if you have the empirical formula, you find the multiple of the mass that gives you the molecular formula, you can calculate what the molecular formula is. So let's go ahead and do a few problems. The first two are pretty easy, but then it gets a little tricky. Okay, so what is the molecular mass of butadiene given that the empirical formula is C2H3O and the molar mass is 86.09? Okay, okay, so this is what we're going to try to do. So we're going to try to get a molecular formula. Now, I'm going to write a blank here. Hopefully we'll get the formula from this compound. And so we do know a molar mass for this compound, which is 86.09 grams per mole. Now, we do know the empirical formula. And so that value, it looks like, is C2H3O. Okay, and so what we don't know about it is we don't really know the mass of the empirical formula. So that's one thing I want to calculate right now. So we really need to know what the molar mass of this empirical formula is, and then see if the molar mass of the molecular formula is a multiple of it. It probably will be. So how do you figure out the mass of the empirical formula? So it's 2 times 12.01. That's the molar mass of carbon in grams per mole. I'm not going to write grams per mole just to make things a little bit quicker. Plus 3, and then the molar mass of hydrogen, 1.008. Again, grams per mole. I'm not going to write that in. And then 1 of oxygen. Okay, so it's going to be 24.02 plus 3.024 plus 15.999. And so let's see what we get really quick. So 24.02 plus 3.024 plus 15.999 looks like here the molar mass of the empirical formula is 43.043 grams per mole. Okay. Now, we know that is not the true molar mass of the compound. The true molar mass of the compound is going to be derived from the molecular formula. So let's see how many times the molar mass in the molecular formula is that of the empirical formula. So we just divide these two numbers. And so you divide it by 86.09 and take the inverse of that. There it is. Yes. So you can see that 86.09 is about 2 times the value of 43.043. So that basically means to get the molecular formula for this compound, we take this empirical formula and multiply each subscript by 2. So the molecular formula for this compound should be C4H6O2. And so that is the correct answer. Okay, let's move on. Benzopyrene has a molar mass of 252 grams per mole and an empirical formula of C5H3. What is the molecular formula? Okay, so let's set this up. Empirical formula. Wait. I find it's better to start with molecular formula. And then have empirical formula after that. That helps a little bit. Okay, so we're trying to find the molecular formula for this compound. Now we are given a molecular mass of 252 grams per mole. And the empirical formula we do know, it's C5H3. So again, what we have to do is find the molar mass of this empirical formula and see how many times the mass of the molecular formula is of that. So that's not too difficult. So we need the molar mass of this compound, and so it's 5 times the molar mass of carbon in grams per mole plus 3 times the molar mass of hydrogen. So it's going to be 60. All right, so far so good. Okay, so I get a molar mass for this empirical formula to be 63.074. Now, how many times is the molar mass of the molecular formula? Let's see. Well, let me try that again. Okay. So I basically see that the molar mass of the molecular formula is 4 times the mass of the empirical formula. So what we need to do is take this empirical formula and multiply all the subscripts by 4. So the molecular formula for this compound should be C20H12. That should be the answer. Okay, let's move on to the next one. What is the molecular formula of a compound? The molar mass is that value, 180 grams per mole approximately, that has the following percent composition by mass. And so we have those percentages of 3 elements there. And this time they're not asking for an empirical formula. They're asking for a molecular formula. But you can bet you're going to probably have to go through the empirical formula first, and then using the molar mass of the compound, then go to the molecular formula. So let's get the empirical formula first. So we have 3 elements, carbon, hydrogen, and oxygen. And I'm not going to write the percent numbers, but use the same number and write it in grams, which we can do. So it's 40.00 grams of carbon, 6.71 grams of hydrogen, 53.29 grams of oxygen. So we divide by the molar mass of carbon, here by the molar mass of hydrogen, and then that of oxygen. Let's see, 15.9. Okay, so let's see what kind of moles we get for each of these elements. So it's going to be 40 divided by 12. 3.331 mole carbon, 6.71. Okay. Okay, so we divide by the smallest one and see we have 3.31 in 2 of them, so that will serve as the smallest one. Okay, so for oxygen, we have 1. For carbon, we have 1. And I can tell, just looking at hydrogen, 6.66 approximately divided by 3.33 is going to be about 2. Okay, so we have a formula so far, but this is an empirical formula. So now we have to go to the next step and get it to the molecular formula. So the empirical formula I'll write up here. It's going to be C1H2O. Now we find the molecular formula. So let me set that up down here. Molecular formula. Now we do have a molar mass from the molecular formula. It is 180.16 grams per mole. And then we have the empirical formula. which is CH2O. Okay, so what we have to do is find the molar mass for the empirical formula. So it's going to be 12.01 grams per mole is the molar mass of carbon, plus 2 times the molar mass of hydrogen, which is 1.008, plus the molar mass of oxygen. Let me get that number really quickly. Okay, so what we get for a molar mass of this empirical formula is 30.025 grams per mole. So let me divide that into 180 and see what we get. Okay, so this is almost exactly 6 times greater than the empirical formula. So we can figure out what the molecular formula is at this point. We know that the mass of the molecular compound is 6 times greater than that of the empirical compound. Therefore, we take this formula, multiply each of these subscripts by 6, and that should be the molecular formula. So the molecular formula should be C6H12O6 for this problem. Thank you for listening. We'll see you next time.